There is a planet at the edge of the solar system that most people forget about entirely. It sits so far from the sun that light itself takes more than 4 hours to reach it. No human technology has ever orbited it. No probe has ever entered its atmosphere. And the one spacecraft that did visit, decades ago, spent less than a single day near its clouds before vanishing into the void. That planet holds the fastest winds ever recorded in the solar system. Winds that will cross the speed of sound on Earth. Its interior crushes molecules into substances that should not exist. And its remoteness is so absolute that a distress signal sent from its cloud tops would not reach anyone for over 4 hours. This is Neptune. And nothing about it wants you there. If this is the kind of science that pulls you deeper, take a second to like and subscribe. We cover what the universe is actually doing, not just what is easy to imagine. Are you comfortable? Now, let's begin. Ask someone to name the planets and count the seconds. Mercury, Venus, Earth, Mars. Most people get that far without thinking. Jupiter comes next because Jupiter is enormous and dramatic and has a storm that has been running for centuries. Saturn follows because its rings are one of the most iconic shapes in all of science. Uranus usually gets a pause and a half smile because of the name. And then, maybe if the person is still trying, they will say Neptune. Maybe. It arrives at the end of the list like an afterthought. The last planet. The one that fills the final slot, not because anyone was excited to reach it, but because the sequence demands that something goes there. Neptune is not the planet people dream about. It is not the planet children draw on poster board with glitter and cotton balls. It is not the planet that inspires movies or dominates the covers of science magazines. Mars gets that attention because Mars feels achievable. Jupiter gets that attention because Jupiter is terrifying, in an obvious and photogenic way. Saturn gets that attention because Saturn is beautiful. Neptune gets almost nothing. It sits at the far edge of the solar system, 30 times farther from the sun than Earth is, wrapped in a blue so deep it looks more like a mood than a colour. And it waits there in a kind of silence that most people never bother to break. That silence is the first clue. Because Neptune is not quiet because it is peaceful. Neptune is quiet because it is so far away, so enormous, and so brutally severe that almost nothing about it has ever been easy to observe, easy to reach, or easy to understand. And the fact that it has been overlooked for so long is not a reflection of what Neptune is. It is a reflection of how limited human attention becomes when the distances involved start to break the imagination. Let us start with what Neptune actually is. Not the postcard version, not the 8th planet trivia answer, the physical object. Neptune is an ice giant. That term matters, and it is often confused with gas giant, which is what Jupiter and Saturn are. The distinction is not cosmetic. Jupiter and Saturn are composed primarily of hydrogen and helium, with deep interiors where hydrogen is compressed into a metallic liquid state that conducts electricity and generates powerful magnetic fields. They are dominated by the lightest elements in the universe, puffed up to extraordinary size by heat and pressure. Neptune is different. Its atmosphere contains hydrogen and helium too, roughly 80% hydrogen and 19% helium by volume, with traces of methane that give the planet its deep blue colour. But beneath that outer envelope, the composition shifts dramatically. Neptune's interior is dominated by heavier volatile compounds, water, ammonia, and methane, compressed under pressures that reach millions of times the atmospheric pressure at Earth's surface. These compounds exist in states that have no everyday analog. They are not ice in the way a frozen lake is ice. They are substances crushed into exotic phases of matter by the sheer weight of everything above them. The word ice in Ice Giant refers to the chemical ancestry of these materials, not their temperature or their texture. Inside Neptune, water does not freeze. It is squeezed into something far stranger than freezing could ever produce. The planet itself is massive. Neptune is approximately 17 times the mass of Earth. Its diameter stretches to roughly 49,500 kilometers, making it nearly 4 times wider than our world. If you could hollow Neptune out and somehow stand inside it, you could fit more than 57 Earths within the volume. And yet, despite being 17 times heavier and nearly 4 times wider, Neptune is not the planet most people think of when they think of giant worlds. Jupiter is 318 times Earth's mass. Saturn is 95 times. Next to those numbers, Neptune's 17 barely registers in casual conversation. It gets treated as a smaller giant, a lesser sibling, a world that is large but not impressively large. That framing is a mistake. 17 Earth masses is not modest. It is enormous. It means Neptune's gravitational pull at the cloud tops is roughly 1.14 times the surface gravity of Earth. A person standing on a hypothetical platform at Neptune's cloud level would weigh about 14% more than they do on Earth. That might sound manageable. It is not the gravity that would destroy you. It is everything else. But before we get to the destruction, we need to understand the distance. Because the distance changes everything about how Neptune exists in the human mind, and it changes everything about what it means to study or visit this world. Neptune orbits the Sun at an average distance of approximately 4.5 billion kilometers. That is roughly 30 astronomical units, meaning it is 30 times farther from the Sun than Earth is. To put that number into proportion, light leaving the Sun takes about 8 minutes to reach Earth. That same light takes over 4 hours to reach Neptune. 4 hours. A beam of light, traveling at 300,000 kilometers per second, the fastest speed anything in the universe can achieve, needs more than 4 hours to cover the gap between the Sun and the 8th planet. Now, consider what that distance means for communication. When Voyager 2 flew past Neptune in August of 1989, every image, every measurement, every byte of data it collected had to travel back to Earth as a radio signal moving at the speed of light. That signal took over 4 hours to arrive. Mission controllers at the Jet Propulsion Laboratory could not steer the spacecraft in real time. They could not make corrections on the fly. Every command had to be sent hours in advance, and every confirmation arrived hours later. The entire flyby was choreographed in advance and executed on faith, because the distances involved made anything resembling a real-time conversation physically impossible. Voyager 2 remains the only spacecraft that has ever visited Neptune. Let that settle for a moment. In the entire history of human spaceflight, in all the decades of robotic exploration that have sent orbiters to Mars, landers to Venus, probes into Jupiter's atmosphere, and a dedicated mission to orbit Saturn for 13 years, Neptune has been visited exactly once. A single flyby, a single spacecraft, a single day of close observation on August 25th, 1989, after a journey of 12 years and roughly 7 billion kilometers. The encounter was extraordinary. Voyager 2, passed within approximately 4,800 kilometers of Neptune's cloud tops, arriving only 22 miles off its charted course and only 1 second off its scheduled time. The precision was remarkable, the engineering was historic, and the data it returned transformed our understanding of this world. Before Voyager 2, Neptune was essentially a blue dot in even the best telescopes. After Voyager 2, it was a planet with storms, rings, a bizarre magnetic field, and a large moon called Triton that appeared to have active geysers erupting nitrogen gas into the vacuum of space. But Voyager 2 did not linger. It could not. The spacecraft was on a trajectory that carried it past Neptune and onward toward interstellar space. There was no braking, no orbit insertion, no second pass. The flyby window lasted less than a day, and when it closed, Voyager 2 was gone, and Neptune returned to being observed only from a distance of 4.5 billion kilometers. That was 1989, more than 3.5 decades ago. In the years since, no spacecraft has returned. No orbiter has been approved. The most recent Planetary Science Decadal Survey, published in the early 2020s, ranked a Uranus orbiter and probe as the top priority flagship mission for NASA, ahead of Neptune. Neptune was considered, a mission concept called Neptune Odyssey was studied and published, proposing a flagship-class orbiter and atmospheric probe to the Neptune and Triton system. But for logistical and cost reasons, Uranus was chosen first. Even among the ice giants, Neptune came second. Even among the neglected, it was more neglected. The reasons are practical. Uranus is closer. A mission to Uranus using a Jupiter gravity assist could launch in the early 2030s and arrive in the mid-2040s. A comparable mission to Neptune would require an even longer cruise, with fewer favorable launch windows and higher energy requirements. The optimal Jupiter gravity assist window for Neptune is narrower and less frequent. Everything about reaching Neptune is harder, slower, and more expensive than reaching its closer sibling. And so Neptune waits. It has been waiting since 1989. It will likely continue waiting for decades more. The data we have from close range is more than 35 years old, collected by a spacecraft that was built in the 1970s and operated on less computing power than a modern key fob. Every detailed image of Neptune that has ever been published came from that one encounter. Every close measurement of its magnetic field, its ring system, its atmospheric structure, and its moon system was collected in a window shorter than a single Earth day. And even collecting that data was not straightforward. By the time Voyager 2 reached Neptune, the spacecraft was so far from Earth that its radio signal had weakened to a whisper. Radio signals obey the inverse square law. Double the distance and the signal strength drops to 1/4. At Neptune's range, the signal arriving at Earth was billions of times fainter than a typical cell phone transmission. To hear it at all, NASA had to physically rebuild parts of the deep space network. The 3 primary tracking antennas, located in California, Spain, and Australia, were expanded from 64 meters to 70 meters in diameter. That 6-meter increase might sound modest. It was not. Widening a steerable radio dish of that size required years of engineering work and significant structural reinforcement, and even the expanded dishes were not enough on their own. NASA enlisted the 64-meter Parkes radio telescope in Australia and arrayed multiple 25-meter antennas at the Very Large Array in New Mexico. combining their signals to squeeze every fraction of usable data from the faint stream arriving from 4.5 billion kilometers away. That is the effort required to listen to a spacecraft that was already at Neptune. Not to send a new one, not to orbit, not to land, just to hear the data from a machine that happened to be passing through. The infrastructure of an entire global tracking network had to be physically modified for a single planetary encounter. And when that encounter ended, the modifications remained. But Neptune was once again beyond the reach of anything that could use them. That is the first layer of what makes Neptune unforgiving. Not the storms, not the cold, not the crushing interior, the distance, the sheer, relentless, numbing distance that separates this world from every instrument, every spacecraft, and every human being that has ever tried to understand it. Neptune does not hide behind clouds or camouflage itself against the background of space. It simply exists so far away that reaching it is one of the most difficult things our species has ever attempted, and we have only managed it once. Now consider what we know about the planet itself, and how much of that knowledge is built on a foundation thinner than almost anyone realizes. Neptune was not discovered by someone looking through a telescope and spotting it by accident. It was predicted mathematically before it was ever seen. In the 1840s, astronomers noticed that Uranus was not behaving as expected. Its orbit showed small but persistent deviations from the path that gravitational calculations predicted. Something unseen was pulling on it. Two mathematicians working independently, Urbain Louvier EA in France and John Couch Adams in England, calculated where a hypothetical eighth planet would need to be to explain the discrepancies. On September 23rd, 1846, the German astronomer Johann Galuh pointed his telescope at the coordinates Louvier EA had provided and found Neptune within 1 degree of the predicted position. It was a triumph of mathematics, a planet discovered not by observation, but by calculation. Gravity itself revealed Neptune's existence before any human eye could see it. That origin story is fitting, because Neptune has remained a world that resists direct observation ever since. It is never visible to the naked eye. Its apparent magnitude is too faint to see without a telescope, making it the only major planet in the solar system that has never been seen by an unaided human being looking up at the night sky. Every other planet, Mercury, Venus, Mars, Jupiter, and Saturn, was known to ancient civilizations because they could be spotted as wandering points of light. Neptune was invisible until the technology existed to find it. It entered human awareness not through wonder or curiosity, but through a mathematical anomaly in the orbit of another planet. Even with modern telescopes, Neptune is extraordinarily difficult to study in detail from Earth. Its angular size in the sky is tiny. Ground-based observations are limited by atmospheric distortion, and even space telescopes like Hubble and the James Webb Space Telescope can only resolve large-scale features. The fine details of Neptune's weather, the structure of its storms, the layering of its atmosphere, remain beyond the reach of anything except a spacecraft close enough to look directly. The James Webb Space Telescope has provided some of the sharpest recent images of Neptune, capturing the planet in near-infrared light and revealing its ring system with a clarity not seen since Voyager 2. Those images, released in 2022, were striking. Neptune appeared not as a vivid blue sphere, but as a ghostly, pale orb surrounded by delicate rings and dotted with bright methane ice clouds. The infrared view strips away the methane blue and shows the planet as a colder, more skeletal version of itself. It was beautiful. It was also a reminder that even our most powerful telescope, parked 1.5 million kilometers from Earth at the second Lagrange point, can only observe Neptune from an almost incomprehensible distance. The detail is impressive by Earth-based standards. By the standards of what we know about Mars or Jupiter or Saturn, it is almost nothing. This is Neptune's first act of hostility. Not a storm, not a temperature reading, silence, distance, absence. The planet is so far away that studying it in any meaningful depth requires sending a machine on a journey measured in decades. And even then, the machine can only stay for hours before the geometry of spaceflight carries it away. Every major planet closer to the Sun has been orbited by a dedicated spacecraft. Mercury has been orbited. Venus has been orbited. Mars has been orbited dozens of times. Jupiter has had Galileo and Juno. Saturn had Cassini for 13 years. Even the dwarf planet Pluto received a dedicated flyby mission designed from the ground up to study it. Neptune has received one visit from a spacecraft that was not designed for it. Voyager 2 was built to explore Jupiter and Saturn. The Neptune flyby was an extended mission, made possible by a rare planetary alignment that allowed the spacecraft to swing from one giant planet to the next using gravity assists. Neptune was the final stop, not the primary destination. The data collected was extraordinary given the constraints, but the constraints were severe. The spacecraft was aging. Its instruments were not optimized for an ice giant. And still, that faint whisper of data told us things we had never imagined. Neptune was not a quiet, frozen world gently circling at the edge. It was a planet in turmoil. Its atmosphere was dynamic, streaked with bands of cloud, punctuated by enormous dark storms, and whipped by winds faster than anything recorded on any other planet. The Great Dark Spot, a storm system the size of Earth, rotated in the southern hemisphere with ferocious energy. Bright white clouds of methane ice streaked past at velocities that defied expectation. The magnetic field was tilted at a wild angle, offset from the planet's center in a way that made no clean geometric sense. And then there was Triton. Triton is Neptune's largest moon, roughly 2,700 kilometers across, and it is one of the most extraordinary objects Voyager 2 encountered on its entire grand tour. It orbits Neptune backward, retrograde. It is the only large moon in the solar system that orbits in the opposite direction to its parent planet's rotation. That single fact tells a violent story. Triton did not form alongside Neptune the way most large moons form alongside their planets, accreting from the same disk of gas and dust. Triton was captured. It was a wanderer from the Kuiper Belt, the vast region of icy bodies beyond Neptune's orbit, and at some point in the distant past, it strayed too close to Neptune's gravitational reach and was seized. The capture was not gentle. The process of gravitational capture requires the incoming body to lose enough orbital energy to become bound, and the most likely mechanism involves tidal interactions so intense that they would have heated Triton's interior to extraordinary temperatures, potentially melting much of the moon from the inside. The capture would also have been catastrophic for whatever original moon system Neptune possessed. Any pre-existing moons in orbits that intersected Triton's new path would have been scattered, ejected, or destroyed. Neptune's current system of small inner moons may have reformed from the debris of that destruction. Triton did not join Neptune peacefully. It was taken, and the taking likely shattered everything that was already there. What Voyager 2 found at Triton was astonishing. The surface temperature was approximately minus 235 degrees Celsius, making it one of the coldest measured surfaces in the solar system. The terrain was young and geologically active, with few impact craters and strange cantaloupe-textured regions unlike anything seen elsewhere. And erupting from the surface, Voyager 2 observed dark plumes of nitrogen gas and dust shooting up to 8 kilometers above the ground, driven by subsurface heating that turned frozen nitrogen into gas. Triton had active geysers. On a moon orbiting a planet 4.5 billion kilometers from the sun, in temperatures that make Antarctica feel tropical, something beneath the surface was generating enough heat to drive eruptions. That heat likely comes from tidal forces. As Triton orbits Neptune on its retrograde path, the gravitational interaction between the two bodies flexes the moon's interior, generating friction and warmth. Some planetary scientists believe this tidal heating may be sufficient to sustain a layer of liquid water beneath Triton's icy crust, making Triton a candidate ocean world. If liquid water exists inside Triton, it joins a small and exclusive list alongside Europa, Enceladus, and possibly Titan as places in the solar system where the conditions for life might theoretically exist. And here is the painful irony. One of the most scientifically compelling moons in the entire solar system, a captured Kuiper belt twin of Pluto, with active geysers and a possible subsurface ocean, orbits the one planet we are least equipped to revisit. Triton has been observed up close exactly once, during the same less-than-a-day flyby window that produced all of our close-range Neptune data. Everything we know about its geysers, its surface geology, and its potential for a hidden ocean comes from that single encounter. No dedicated mission has ever studied it. None is currently approved. Every one of Voyager 2's findings raised more questions than it answered. And then Voyager 2 left, and the questions hung in the vacuum, unanswered, for decades. The planet completes one orbit around the Sun every approximately 165 Earth years. That means Neptune has completed roughly one full orbit since it was discovered in 1846. One single trip around the Sun in the entire span of human awareness. We have known Neptune for exactly one of its years. We have visited it for less than one of its days. And the gap between what we know and what we do not know is so vast that it makes the 4.5 billion kilometers between Neptune and Earth feel like a metaphor for something worse than physical distance. Neptune rotates once every approximately 16 hours and 6 minutes. Its day is shorter than Earth's. That means its storms, its winds, its atmospheric chaos cycle faster than ours, compressed into a rotation that spins the cloud tops at speeds that amplify the violence already present in the atmosphere. A 16-hour day on a planet 17 times the mass of Earth, with the fastest winds in the solar system, is not a comfortable rhythm. It is a centrifuge. Neptune also has rings, faint, narrow, and clumpy, nothing like the broad, bright bands of Saturn. The rings were suspected before Voyager 2 arrived, based on ground-based stellar occultation data that showed partial blockages suggesting incomplete arcs rather than full rings. Voyager confirmed them, revealing a system of at least 5 rings composed of dust and small particles, some concentrated in dense clumps called ring arcs. The rings are dark and difficult to see. Another feature of Neptune that refuses to present itself clearly. Everything about this planet resists easy engagement. Its distance resists travel. Its faintness resists observation. Its atmosphere resists understanding. Its interior resists modeling. Its magnetic field resists simple geometry. And its place in the cultural imagination resists even basic familiarity. Neptune is the planet that most educated adults can name but cannot describe. It occupies the last slot in the sequence, and then fades from thought the moment the list is complete. That fading is the mistake this entire story is built to correct, because Neptune is not mild. It is not boring. It is not simply the last and least. It is one of the most violent, most extreme, most physically hostile worlds in the entire solar system. And the fact that it sits so far away that most of its violence goes unwitnessed does not make it less severe. It makes it more so. A storm you can see is a storm you can study, track, and prepare for. A storm 4.5 billion kilometers away, raging at supersonic speeds in temperatures that would freeze nitrogen solid, in an atmosphere that crushes everything beneath it into alien states of matter, is a storm that exists entirely beyond your ability to respond. Neptune does not care that you forgot about it. Neptune does not need your attention to keep raging. And what we are about to describe is a world so comprehensively hostile that the only thing more disturbing than its violence is the realization that almost no one is watching it happen. The storms are coming, and they are worse than you think. Here is what scientists expected to find when Voyager 2 approached Neptune in the summer of 1989. They expected almost nothing. The reasoning was straightforward, and at the time, widely accepted. Neptune receives approximately 900 times less solar energy per unit area than Earth does. At 30 astronomical units from the Sun, the light that reaches Neptune is so feeble that noon on Neptune would look like deep twilight on Earth. The Sun, from Neptune's cloud tops, appears as little more than an unusually bright star, a point of light that provides roughly 1/900th of the warmth that drives weather systems on our own planet. Given that lack of energy input, atmospheric scientists assumed Neptune would be docile. The prevailing thinking was simple. Weather requires energy. Less energy means less weather. Neptune, sitting in the frozen dark at the edge of the planetary system, should have been one of the calmest atmospheres in the solar system. Uranus, which is closer to the Sun and receives more energy, had already been visited by Voyager 2 3.5 years earlier. Its atmosphere was bland, almost featureless, a pale blue-green sphere with barely any visible cloud structure. If Uranus was that quiet, Neptune, farther away and colder, should have been a frozen whisper. Voyager 2 arrived and the whisper turned out to be a scream. The first high-resolution images returned from Neptune revealed an atmosphere in violent motion. Bands of cloud streaked across the planet at different speeds and different latitudes. Bright white features, later identified as high-altitude methane ice clouds, raced through the upper atmosphere, casting shadows on the deeper cloud layers beneath them. And dominating the southern hemisphere was an enormous oval storm, dark against the surrounding blue, roughly 13,000 kilometers across, large enough to swallow the entire Earth. They called it the Great Dark Spot. The name was a deliberate echo of Jupiter's Great Red Spot, which had been observed for centuries and had become one of the most recognizable features in planetary science. But the comparison was misleading in an important way. Jupiter's Great Red Spot is stable. It has persisted for at least 350 years, likely much longer. It is a permanent fixture of Jupiter's atmosphere, a storm so entrenched in the fluid dynamics of the planet that it has become effectively immortal on human timescales. Neptune's Great Dark Spot was nothing like that. When the Hubble Space Telescope turned its instruments toward Neptune in 1994, 5 years after Voyager 2's flyby, the Great Dark Spot was gone. It had vanished completely. Not weakened, not shifted position. Vanished. An Earth-sized storm system had appeared, raged with extraordinary violence, and then dissolved back into the atmosphere as though it had never existed. And in the northern hemisphere, a new dark spot had formed. Neptune had replaced one giant storm with another, in a different location, in less than 5 years. This pattern has continued for decades, and tracking it from across the solar system has become one of the more humbling exercises in modern planetary science. In 1994, the same year Hubble confirmed the disappearance of the original Great Dark Spot, astronomers identified a new storm in Neptune's northern hemisphere, designated the Northern Great Dark Spot. It was smaller than its predecessor, but still enormous, thousands of kilometers across, and it was accompanied by bright white companion clouds made of methane ice, pulled upward by the storm's dynamics the way thunderheads billow above a hurricane on Earth. Those bright companions became one of the few reliable ways to track dark spots from such an immense distance. Because the methane ice clouds catch the feeble sunlight and glint like beacons marking something far larger and darker beneath. Through the 2000s and 2010s, Hubble and ground-based adaptive optics telescopes continued to monitor Neptune's atmosphere, catching glimpses of new dark spots forming, drifting across latitudes, and then fading. In 2018, Hubble observed a dark spot in the northern hemisphere that appeared to be shrinking, tracked its movement over multiple observation sessions, and watched it dissolve over the course of roughly 2 years. Another dark storm was observed migrating southward toward the equator, a trajectory that some models suggested should be impossible given the planet's atmospheric circulation patterns. Neptune's storms do not obey the predictions. They form where models say they should not form. They move in directions that challenge the simulations, and they vanish on timescales that are shockingly brief for a planet of this size, leaving no visible trace of their existence in the surrounding cloud bands. The difficulty of observing these storms cannot be overstated. From Earth, even with the most powerful telescopes available, Neptune is a tiny disk. Resolving a storm system thousands of kilometers across requires observations at the edge of instrumental capability. Cloud features come and go between observation sessions that may be separated by weeks or months, because telescope time on instruments powerful enough to resolve Neptune is limited and shared among thousands of competing astronomical programs. The result is a record that is detailed by the standards of outer planet science and hopelessly incomplete by the standards of atmospheric science. We know that Neptune's storms cycle, we know they are enormous, we know they are transient, but we do not know how they form, how long they typically last, what triggers their dissolution, or what happens in the atmosphere between the observation windows we were able to capture. Neptune's weather is a book we are reading one sentence at a time, with pages missing between each one. Jupiter builds permanent monuments out of its storms. Neptune builds temporary explosions and then erases them. The storms alone would be remarkable. But the storms are not what earned Neptune the title of the windiest planet in the solar system. The winds did. When Voyager 2 measured Neptune's atmospheric dynamics, the numbers that came back were difficult to believe. The equatorial winds on Neptune blow in the retrograde direction, opposite to the planet's rotation, at sustained speeds exceeding 1,200 miles per hour. That is approximately 2,000 kilometers per hour. Let those figures exist for a moment. On Earth, the most powerful hurricanes, Category 5 storms that flatten cities and tear steel-reinforced buildings from their foundations, produce sustained winds of roughly 157 miles per hour at their lower threshold. The strongest tornado ever measured on Earth, an EF5 event, generated wind speeds estimated at around 318 miles per hour. Neptune's sustained equatorial winds are nearly 4 times faster than the most violent tornado ever recorded on our planet. And on Neptune, those are not the peak gusts inside a storm. Those are the background conditions, the baseline, the normal state of the atmosphere. The wind speeds measured near the Great Dark Spot were even more extreme. Estimates based on Voyager 2's cloud tracking data placed localized wind speeds in the vicinity of the storm at up to 2,400 kilometers per hour. At those velocities, the atmosphere is not simply moving fast. It is moving at speeds that, if they occurred in Earth's atmosphere, would exceed the speed of sound. On Earth, the speed of sound at sea level is roughly 1,235 kilometers per hour. Neptune's peak winds are nearly double that figure. The only reason they do not technically break the sound barrier on Neptune is that the speed of sound depends on the density and composition of the medium, and Neptune's hydrogen-helium atmosphere is dense enough that the local speed of sound is higher than it would be in Earth's air. The winds are not supersonic on Neptune, but translated into terrestrial terms, they are beyond anything that exists in the human experience of weather. There is nothing on Earth that prepares you for this. The worst hurricanes, the most destructive tornadoes, the most violent windstorms ever recorded in human history are slow, gentle events compared to the ambient conditions on Neptune. A wind of 2,000 kilometers per hour is not weather. It is demolition at planetary scale, sustained continuously, wrapping the entire equatorial band of a world 4 times wider than Earth. And the deepest paradox is this: no one fully understands where the energy comes from. Neptune receives approximately 1/900th the solar energy that Earth receives. That is not enough to drive weather systems of this magnitude. On Earth, the sun is the engine of all weather. Solar radiation heats the surface unevenly, creating temperature gradients that drive convection, which drives wind, which drives storms. The energy budget is straightforward. More sunlight equals more energy equals more atmospheric activity. Neptune violates this equation. Its atmosphere is more violent than Jupiter's, a planet that is 5 times closer to the sun and receives 25 times more solar energy per unit area. Neptune's winds are 3 times stronger than Jupiter's and 9 times stronger than Earth's, despite receiving a fraction of the solar input that either of those worlds gets. Something else is powering the machine, and this is where the comparison with Uranus becomes genuinely strange, because Uranus makes the puzzle worse rather than better. Neptune and Uranus are often described as twins. They are similar in mass. Uranus is roughly 14.5 Earth masses. Neptune is roughly 17. They are similar in diameter. Uranus is about 51,000 kilometers across. Neptune is about 49,500. They're both ice giants with interiors dominated by water, ammonia, and methane rather than the metallic hydrogen of Jupiter and Saturn. Their atmospheric compositions are nearly identical. Their bulk densities are close. If you place their specification sheets side by side and remove the names, you would be tempted to call them the same type of planet built to slightly different proportions. And yet, their atmospheres could not be more different. When Voyager 2 flew past Uranus in January of 1986, the images returned were startling in their blandness. Uranus presented a nearly featureless disk, a pale blue-green sphere with almost no visible cloud structure, no banding, no storms, no atmospheric drama of any kind. The atmosphere appeared calm to the point of dormancy, as though the planet had simply decided not to participate in weather. Later observations with Hubble and ground-based telescopes did reveal some cloud activity, particularly as Uranus approached its equinox in 2007 and more of its atmosphere became illuminated. But even at its most active, Uranus is atmospherically subdued compared to Neptune. Its wind speeds are significant but well below Neptune's extremes. Its storms, when they appear, are smaller and less violent. The critical difference is internal heat. Uranus radiates almost no excess energy. Measurements show that Uranus emits roughly the same amount of thermal energy as it receives from the Sun, or perhaps slightly more. Something about its interior has shut down the heat engine that drives atmospheric dynamics on the other giant planets. Researchers have proposed several explanations. One hypothesis suggests that a massive impact early in Uranus's history, the same impact that may have knocked the planet onto its side, disrupted the internal layering that allows heat to escape efficiently. Another suggests that the interior of Uranus has stratified into stable layers that inhibit convection, trapping heat deep inside where it cannot reach the atmosphere. Whatever the mechanism, the result is clear. Uranus keeps its internal heat locked away, and its atmosphere pays the price in silence. Neptune does the opposite. Neptune radiates approximately 2.6 times more energy into space than it receives from the Sun. This is a measured fact, confirmed by Voyager 2's infrared instruments. The planet is generating its own heat, bleeding thermal energy outward from its interior at a rate that significantly exceeds the energy arriving from outside. That internal heat source is what drives the atmospheric violence. This contrast is one of the most important unsolved problems in planetary science. Two planets that are nearly identical in size, mass, and composition produce atmospheres that are wildly different. One is a frozen whisper. The other is the most violent wind environment in the solar system. The difference comes down to internal heat, and the internal heat comes down to whatever is happening thousands of kilometers below the cloud tops, in regions no instrument has ever observed directly. Neptune's violence is not a generic feature of ice giants. It is something specific to Neptune, something that even its nearest sibling does not share, and something that science still cannot fully explain. The exact mechanism driving Neptune's excess heat is still debated. The most widely accepted explanation involves gravitational contraction and differentiation. As heavier materials in Neptune's interior slowly sink toward the core and lighter materials rise, gravitational potential energy is converted into thermal energy. This process, called Kelvin-Helmholtz contraction, releases heat over billions of years. Neptune may still be cooling from its formation 4.5 billion years ago, radiating the remnant thermal energy of its gravitational collapse, supplemented by the ongoing settling of denser materials within its interior. There is also the possibility that chemical processes deep inside the planet contribute. When methane molecules are subjected to the extreme pressures found thousands of kilometers below the cloud tops, they can be torn apart, liberating hydrogen and leaving carbon atoms to be compressed into denser structures. That chemical decomposition releases energy, and the substances it produces, including solid diamonds, sink further into the interior, releasing additional gravitational energy as they descend. Neptune may be partially powered by the destruction of its own chemistry, a planet that dismantles molecules and converts the wreckage into heat. Whatever the combination of mechanisms, the result is clear. Neptune has an internal furnace, and that furnace drives weather that is not merely extreme by outer planet standards. It is the most extreme wind environment in the entire solar system, located on a planet that, by every surface level expectation, should have been calm. This is the part that makes atmospheric scientists uncomfortable. Not the speed of the winds, not the size of the storms, the fact that the violence was not predicted. The models said Neptune should be quiet. The mathematics of solar energy input said there was not enough fuel. And when Voyager 2 arrived and showed us a raging atmosphere with the fastest winds ever measured, it exposed a gap in our understanding that has never been fully closed. We still cannot reproduce Neptune's atmospheric dynamics in computer models with full confidence. The internal heat helps explain the energy budget, but the specific mechanisms that convert that heat into such extreme wind speeds, concentrated in the outermost fraction of 1% of the planet's mass, remain an open and active area of research. The winds are confined to a surprisingly thin layer. Studies of Voyager 2's trajectory data, which measured subtle gravitational variations as the spacecraft passed Neptune, revealed that the high-speed winds occupy only the outermost 0.2% of the planet's mass. That is a shell roughly 1,100 kilometers deep, sitting on top of a vastly deeper interior that rotates as a more rigid body. The ferocity of Neptune's weather is a surface phenomenon in the literal sense. It is a thin, screaming skin wrapped around an interior that moves differently. The shear between these layers, the difference in velocity between the howling upper atmosphere and the slower rotating bulk beneath, is itself a source of enormous mechanical energy. Now consider the color. Neptune is blue. Not the blue of Earth's oceans, which is caused by the absorption and scattering of sunlight by liquid water. Neptune's blue is caused by methane. The trace amount of methane in Neptune's upper atmosphere, roughly 1 to 2% by volume, absorbs red wavelengths of sunlight and reflects blue wavelengths back into space. The result is a deep, rich azure that is one of the most striking colors in the solar system. But for decades, Neptune was believed to be much bluer than it actually is. The iconic images from Voyager 2, the ones that appeared in textbooks and documentaries for more than 30 years, were color enhanced. The Voyager imaging team had processed the photographs to increase contrast and reveal cloud features that would otherwise be invisible against the uniform blue background. This was done deliberately and for good scientific reasons, but it left the public with an image of Neptune that was more vivid than reality. In 2024, researchers reprocessed the original Voyager 2 data using modern techniques and published corrected color images. The real Neptune is still blue, but it is a paler, gentler blue, closer to the hue of Uranus than most people realized. The two ice giants, it turns out, look more alike than the old photographs suggested. That correction matters because it reinforces something important about Neptune. Even the way we see this planet has been shaped by the difficulty of observing it. The colours were wrong for decades. The atmospheric dynamics were not predicted. The storms come and go without warning. Neptune resists accurate perception at every level, not because it is trying to deceive, but because the distance and the difficulty of observation make every piece of information incomplete, delayed, or filtered through technology that was never fully designed for the task. And then there is the magnetic field. If the winds are Neptune's most dramatic atmospheric feature, the magnetic field is its most disorienting structural one. On Earth, the magnetic field is generated by convection currents in the liquid iron outer core. The field is roughly aligned with the planet's rotation axis, tilted by about 11 degrees. This alignment means that the magnetic poles are relatively close to the geographic poles. Compasses work. The magnetosphere is roughly symmetric. The interaction between the magnetic field and the solar wind produces a protective bubble around the planet that is stable, predictable, and geometrically clean. Neptune's magnetic field is none of those things. It is tilted approximately 47 degrees from the planet's rotation axis, and it is not centered on the planet's core. The magnetic center is offset from the geometric center of Neptune by roughly half the planet's radius, displaced toward the southern hemisphere. The result is a magnetic field that does not wrap symmetrically around the planet. Instead, it creates a magnetosphere that is wildly asymmetric, with field strengths that vary enormously depending on where you are on or around the planet. As Neptune rotates on its 16-hour cycle, this tilted off-center magnetic field tumbles through space like a spinning top that has been knocked sideways. The magnetosphere does not maintain a stable orientation relative to the incoming solar wind. It wobbles, it flips, it corkscrews through the plasma environment in a pattern so complex that modeling it requires accounting for the planet's rotation, the field's tilt, the field's offset, and the interaction with charged particles streaming from the sun all at once. When Voyager 2 first measured this field, the assumption was that something about Neptune's interior must be unique. A magnetic field that lopsided had to be the result of unusual internal conditions. But then, Voyager 2 had already measured a similarly bizarre magnetic field at Uranus, which is tilted about 60 degrees from its rotation axis and also offset from the planet's center. Two ice giants, both with wildly tilted and offset magnetic fields. That suggested the geometry was not a fluke. It was a feature of ice giant interiors. The leading explanation ties the magnetic field directly to the exotic states of matter inside the planet. On Earth, the magnetic dynamo operates in a deep, liquid iron core. On Neptune, there is no liquid iron core generating the field. Instead, researchers believe the dynamo operates in a shallower layer, a region where water, ammonia, and methane exist under such extreme pressures that they become electrically conductive. This layer is not at the center of the planet. It is offset, located in the mantle rather than the core, and its geometry, driven by the specific distribution of conductive fluids within Neptune's interior, produces a magnetic field that reflects the asymmetry of its source. Recent experimental work has strengthened this picture. In 2024 and 2026, researchers at the SLAC National Accelerator Laboratory and other facilities published studies mapping the structure of superionic water, the bizarre high-pressure phase of water that exists deep inside ice giants. In this state, oxygen atoms lock into a rigid crystal lattice, while hydrogen ions flow freely through the structure like a liquid. This hybrid material conducts electricity remarkably well, and the flow of those charged hydrogen ions through the solid oxygen framework is now believed to be a primary driver of the magnetic dynamo inside Neptune and Uranus. The strange, messy internal structure of superionic water may directly explain why the magnetic field is so strange and messy from the outside. The practical consequence of this tumbling, asymmetric magnetosphere is that Neptune's space environment is chaotic. Charged particles from the solar wind interact with the magnetic field differently at every point in the planet's rotation. Radiation belts form and shift unpredictably. The boundary between Neptune's magnetic influence and the surrounding solar wind, called the magnetopause, moves and deforms on a 16-hour cycle. Any spacecraft attempting to orbit Neptune would need to account for a magnetic environment that is not merely hostile, but continuously reconfiguring itself. This is not a detail. This is a structural feature of the planet that makes it unlike anything in the inner solar system. Earth's magnetosphere is a shield. Jupiter's magnetosphere is a weapon, accelerating charged particles to lethal energies across a radiation zone that can damage spacecraft electronics in hours. Neptune's magnetosphere is something stranger. It is a wobbling, asymmetric, off-center magnetic cage that tumbles through space, reshaping itself with every rotation, driven by a dynamo that operates in the material that did not even have a confirmed laboratory existence until recently. Put it together. Step back and look at what Neptune presents to any object, any instrument, any hypothetical visitor entering its domain. The atmosphere greets you with winds that would be supersonic on Earth. Not gusts, not storm peaks. Sustained, planet-wide flows that exceed 2,000 kilometers per hour. Storms the size of Earth form without warning and dissolve just as suddenly, cycling through the atmosphere in patterns that no model fully predicts. The temperature at the cloud tops sits at approximately minus 218 degrees Celsius. The methane ice clouds that streak through the upper atmosphere are moving so fast that tracking them requires time-lapse photography, even from a passing spacecraft. Below the clouds, the pressure rises. Within a few hundred kilometers, you're in an environment where the atmospheric density increases to the point that the distinction between gas and liquid begins to blur. There is no solid surface. There is no ground. There is only a deepening compression, a transition from atmosphere to fluid, to something denser and stranger, with no boundary you could stand on, no horizon you could see, and no moment where you could say you had arrived anywhere. The magnetic field surrounds you, but it does not protect you the way Earth's field protects its surface. It tumbles, it shifts. The radiation environment changes with every rotation of the planet beneath you. The magnetopause flexes and retreats, sometimes exposing regions of near Neptune space to the unfiltered solar wind and the light. At 30 astronomical units from the Sun, the light reaching Neptune is approximately 1/900th as intense as the light reaching Earth. The Sun is a bright star, nothing more. At the cloud tops, the illumination is roughly equivalent to a dim civil twilight on Earth. You could read by it, but only barely. Deeper into the atmosphere, the light fades quickly. Within a few hundred kilometers below the cloud tops, it is completely dark. The interior of Neptune, where the real violence happens, where molecules are torn apart and diamonds are forged, and water is crushed into alien crystal lattices, exists in total blackness. Nothing that happens inside this planet happens in the light. This is what the silence hides. This is what sits at the end of the solar system, behind the charisma of Jupiter and the beauty of Saturn, past the oddity of Uranus, in a region of space so remote that sunlight arrives as a rumor. Neptune is not calm. It is not a frozen ornament placed at the boundary of the planetary system for decorative symmetry. It is a world of continuous, extraordinary violence, powered by its own internal heat, shaped by pressures that produce materials no earthly laboratory can sustain for more than fractions of a second, wrapped in a magnetic field that defies simple geometry and whipped by winds that would obliterate anything humans have ever built. And we have seen it up close exactly once, for less than a day. With a spacecraft built before most of the people hearing this were born, everything described so far, every wind speed, every storm, every magnetic measurement, comes from that single encounter or from telescopic observations made across a gulf of 4.5 billion kilometers. The picture is extraordinary given those constraints. It is also, by any honest assessment, incomplete. We do not know what Neptune's atmosphere looks like on a continuous basis. We do not know how its storms evolve over years and decades. We do not know the fine structure of its magnetic field or the precise chemistry of its deep interior. We have snapshots, we have inferences, we have models that do not fully work. What we know for certain is that Neptune's atmosphere is the most violent wind environment in the solar system, that its storms are powerful and transient, that its internal heat defies the expectation set by its distance from the sun, and that its magnetic field operates on principles that are still being confirmed in laboratories. What we also know, and what the Uranus comparison makes painfully clear, is that this violence is not simply what ice giants do. It is what Neptune does. Its near twin next door sits in comparative silence, its heat locked away, its atmosphere muted. Neptune alone among the ice giants has chosen, if a planet can be said to choose, to burn from the inside and scream from the outside. What we are about to enter next is the interior, the place beneath the clouds, beneath the winds, beneath the last traces of light, the place where pressure remakes matter itself. And what happens down there is not just hostile. It is a kind of hostility that has no comparison anywhere in human experience. Imagine descending, not through air, not through water, but through something that begins as one and slowly becomes the other without any boundary you could identify. There is no surface on Neptune. There is no moment where a spacecraft or a probe or a hypothetical human body transitions from outside to inside. The atmosphere does not end. It thickens, it deepens, it compresses. What starts as a thin haze of hydrogen and helium at the top of the cloud deck gradually becomes denser, hotter, and more opaque with every kilometer of descent. The gas becomes a fluid. The fluid becomes a dense, hot slurry, and the slurry eventually becomes something that no longer resembles any substance familiar to life on Earth. This is Neptune's interior. And understanding what happens inside it requires abandoning almost every physical intuition a human being carries from living at the bottom of Earth's thin, gentle atmosphere. Start at the cloud tops. The temperature there is approximately minus 218 degrees Celsius. The pressure is roughly 1 bar, comparable to sea level pressure on Earth. This is the last point at which conditions are even remotely recognizable. From here, everything gets worse, and it gets worse fast. Descend 100 kilometers. The pressure has already risen to several bars. The temperature is climbing. The hydrogen-helium atmosphere is growing denser, and traces of methane, ammonia, and hydrogen sulfide are becoming more concentrated. The blue color of the upper atmosphere fades because there is no longer enough sunlight to create it. Within a few hundred kilometers of the cloud tops, you are in total darkness. Whatever remains of the sun's faint illumination has been scattered and absorbed by the thickening gas above. From this point on, everything that happens inside Neptune happens in the dark. Descend further, 1,000 kilometers below the cloud tops. The pressure has risen to dozens of bars. The temperature has climbed to several hundred degrees Celsius. The atmosphere around you is no longer a gas in any conventional sense. It is a supercritical fluid, a state of matter where the distinction between liquid and gas ceases to exist. The molecules are packed too tightly to behave like a gas, but too energetic to settle into a liquid. The substance surrounding you has the density of a thick fluid, but no surface tension, no meniscus, no boundary layer. You are not falling through air anymore. You are sinking into a material that grows continuously heavier and hotter with every meter of descent. By the time you reach a depth of roughly 5,000 kilometers, the conditions have entered territory that pushes the limits of laboratory physics. Pressures have risen into the range of hundreds of thousands of atmospheres. Temperatures exceed 2,000 degrees Celsius. The hydrogen and helium that dominated the upper atmosphere have given way to a region where heavier molecules prevail. Water, ammonia, and methane, the defining compounds of an ice giant, exist here under pressures so extreme that their molecular behavior is fundamentally altered. This is the mantle of Neptune. Not a mantle of rock, like Earth's, but a mantle of hot, dense, electrically conductive fluid composed of compounds that on Earth would be ordinary household substances. Water, ammonia, methane. On Earth, these are a glass of drinking water, a cleaning product, and the gas that comes out of a kitchen burner. Inside Neptune, at these pressures and temperatures, they are something else entirely. They are the building materials of an alien engine. Consider the methane first. Methane is a simple molecule, one carbon atom bonded to 4 hydrogen atoms. It is stable under ordinary conditions. It burns easily. It exists as a gas at room temperature and atmospheric pressure. Inside Neptune, thousands of kilometers below the cloud tops, methane molecules are subjected to pressures exceeding 100 gigapascals, roughly 1,000,000 times the atmospheric pressure at Earth's surface, and temperatures of several thousand degrees Celsius. Under these conditions, the molecular bonds that hold methane together cannot survive. The molecule is torn apart. The 4 hydrogen atoms are stripped away, and the carbon atom, suddenly free, is compressed by the surrounding environment into its densest possible crystalline form, diamond. The carbon atoms, liberated from their methane prisons by pressure and heat, are squeezed into the rigid tetrahedral lattice of crystalline carbon. They form diamonds. Not metaphorical diamonds, not diamond-like carbon, actual solid diamonds, nucleating in the crushing darkness of Neptune's interior, and then sinking, slowly, under their own weight, through the surrounding fluid, falling deeper into the planet like a strange and glittering rain that no eye will ever see. This is not speculation. In 2017, researchers at the SLAC National Accelerator Laboratory in California used an ultra-powerful X-ray laser to subject polystyrene, a hydrocarbon plastic with a chemical composition similar to methane, to Neptune-like pressures of approximately 150 gigapascals. The result was the rapid formation of nanodiamonds, tiny diamond crystals that appeared in mere nanoseconds. The lead researcher, Dominic Krauss, described it as one of the best moments of his scientific career. The experiment demonstrated that under the conditions found deep inside ice giants, the conversion of carbon into diamond is not just possible, it is essentially inevitable. Follow-up experiments in 2022 and 2024 expanded the picture further. Researchers found that the presence of oxygen, which is abundant in Neptune's interior because of the vast quantities of water present there, actually lowers the pressure and temperature thresholds required for diamond formation. This means diamonds can form across a wider range of conditions inside Neptune than originally predicted. The diamond rain is not confined to a narrow layer. It likely occurs throughout a significant fraction of the planet's mantle. A continuous precipitation of crystallized carbon falling through hot, dark, pressurized fluid for thousands of kilometers. On Neptune, these diamonds could grow far larger than the nanodiamonds produced in the laboratory. The interior provides millions of years of sustained pressure and temperature, allowing crystals to accumulate and grow. Some researchers have estimated that individual diamonds inside Neptune could reach masses of millions of carats. They would sink through the mantle over geological time, eventually accumulating near the core, forming a layer of solid diamond surrounding whatever rocky or metallic material exists at the very center of the planet. A layer of diamond around the core. That sentence should feel alien, and it should, because there is no equivalent process anywhere in human experience. The interior of Neptune takes one of the most prized substances in human civilization, a material we associate with luxury, permanence, and beauty, and produces it as a waste product of molecular destruction, raining it endlessly into a place no instrument will ever reach. And the diamond rain is not even the strangest thing happening inside this planet. Go deeper. Below the methane dissociation zone, below the region where diamonds form and fall, you enter the domain of water. Not liquid water, not ice, superionic water. Water inside Neptune exists at pressures exceeding 100 gigapascals and temperatures of several thousand Kelvin. Under these conditions, the water molecule does something that has no analog in everyday experience. The oxygen atoms, crushed by the immense pressure, lock into a rigid crystalline lattice, a solid framework that holds its shape the way a metal or a mineral would. But the hydrogen atoms, lighter and more mobile, are ripped free from their bonds with the oxygen and become ions, positively charged particles that flow through the oxygen lattice like a liquid flowing through a solid scaffolding. The result is a substance that is simultaneously solid and liquid. The oxygen component is frozen in place. The hydrogen component streams freely through it. This material conducts electricity with remarkable efficiency because the flowing hydrogen ions carry electrical charge through the solid framework the way electrons carry charge through a copper wire. It is a form of matter that exists nowhere on Earth's surface, nowhere in Earth's interior, and nowhere in any environment that human beings have ever directly experienced. Superionic water was first predicted by theoretical models in 1988. For decades, it remained a computational curiosity, a prediction that could not be verified because no laboratory could sustain the required pressures and temperatures for long enough to observe the material directly. Then, beginning in the late 2010s and continuing through the 2020s, a series of experiments using diamond anvil cells and high-powered lasers began to confirm the prediction. Researchers at Lawrence Livermore National Laboratory, the SLAC facility, and other institutions create fleeting samples of superionic water by compressing ordinary water to pressures exceeding 150 gigapascals while simultaneously heating it with laser pulses. The experiments lasted nanoseconds, billionths of a second. That was long enough to observe the phase transition and confirm that superionic water is real. But the brevity of these experiments underscores a critical point about Neptune's interior. The conditions required to create this material can only be sustained in a laboratory for fractions of a microsecond. Inside Neptune, those same conditions persist continuously across a mantle layer thousands of kilometers thick, sustained by the weight of the planet itself for billions of years. The laboratory creates a flash of superionic water and calls it a breakthrough. Neptune has been filled with the substance since before life existed on Earth. In January of 2026, researchers published new findings mapping the detailed atomic structure of superionic water for the first time. What they discovered was more complex than expected. Rather than forming a single, clean crystal arrangement, the oxygen lattice assembles into a hybrid structure combining two different crystalline patterns, face-centered cubic and hexagonal close-packed layers, with stacking faults and defects scattered throughout. The material is messier than theorists predicted. And that messiness matters because the way charged hydrogen ions flow through a disordered lattice differs from the way they flow through a perfect one. The defects may channel or redirect the ionic currents, affecting how efficiently the material generates magnetic fields. This connects directly to one of the deepest unsolved problems about Neptune. The planet's bizarre magnetic field, tilted 47 degrees from the rotation axis and offset from the planet's center, is generated somewhere inside this superionic mantle. The dynamo that produces the field is driven not by liquid iron, as on Earth, but by the flow of charged hydrogen ions through the solid oxygen scaffolding of superionic water. The geometry of that flow, its speed, its direction, its interaction with the planet's rotation, determines the geometry of the magnetic field above. If the superionic layer is disordered and structurally complex, then the dynamo it produces will be disordered and structurally complex. The lopsided tumbling magnetic field that Voyager 2 measured from the outside may be a direct reflection of the chaotic crystal structure of the material, generating it from the inside. Neptune's magnetic weirdness, in other words, may be a consequence of the fact that the substance producing the field is itself a form of matter that only barely holds together in a coherent structure. Below the superionic mantle, at the very center of Neptune, there is believed to be a core. Its composition is uncertain. Models suggest it is likely composed of rock and metal, possibly similar in composition to the rocky planets of the inner solar system, but compressed to extraordinary density by the weight of everything above it. The temperature at the core is estimated at approximately 5,100 degrees Celsius, comparable to the surface temperature of the Sun. The pressure exceeds 700 gigapascals, roughly 7 million times the atmospheric pressure at Earth's surface. No instrument has ever measured these conditions directly. No experiment has perfectly replicated them. The core of Neptune is inferred from gravitational measurements, from models of planetary formation, and from laboratory experiments that attempt to extend known physics into regimes where direct confirmation is impossible. It is one of the least known objects in the solar system, a region the size of Earth buried beneath thousands of kilometers of superionic water, surrounded by a rain of diamonds, wrapped in an atmosphere of supersonic winds, and separated from the nearest human being by 4.5 billion kilometers of vacuum. Now, consider what it would mean to try to study this interior directly. Not from a distance, not through models or laboratory analogs, with an actual machine sent into the atmosphere, falling through the layers we have just described. We have done this once before at a giant planet. In December of 1995, the Galileo spacecraft released an atmospheric probe into Jupiter's clouds. The probe was purpose-built for the task. It carried a heat shield designed to survive one of the most violent atmospheric entries ever attempted, decelerating from roughly 47 kilometers per second to subsonic speed in less than 2 minutes, while enduring temperatures on the shield face exceeding 15,000 degrees Celsius. Hotter than the surface of the sun, the probe survived the entry. It deployed a parachute, and for approximately 57 minutes, it transmitted data on Jupiter's atmospheric composition, temperature, pressure, wind speed, and cloud structure as it descended through the upper layers. Then, it went silent. The pressure and temperature destroyed it. The Galileo probe reached a depth of roughly 150 kilometers below Jupiter's visible cloud tops before its signal stopped. It had measured conditions down to about 23 bars of pressure and temperatures approaching 150 degrees Celsius. Those numbers might sound extreme by Earth standards. By Neptune's interior standards, they are barely the first step through the door. An atmospheric probe at Neptune would face a related but distinct set of challenges, and in several ways the problem is harder. The entry phase alone would be formidable. A probe arriving at Neptune from an interplanetary trajectory would be traveling at enormous speed relative to the planet, and it would need to decelerate through a hydrogen-helium atmosphere that, at the cloud tops, is thin enough to make aerodynamic braking difficult before conditions become dense enough to make it violent. The heat shield design would need to account for entry dynamics that have never been tested at an ice giant, because no probe has ever entered one. Assuming the probe survives entry and begins its descent, it enters a world with no bottom. This is one of the fundamental differences between landing on a rocky planet and descending into a gas or ice giant. On Mars, a lander targets a surface. On Venus, the Venera probes fell through thick clouds and oppressive heat, but they arrived at solid ground, however briefly. On Neptune, there is no arrival. There is only a continuous deepening. The probe would fall through the methane ice cloud layer, through the hydrogen-helium envelope as it thickens and heats, through the transition into supercritical fluid, and every second of the descent would bring higher pressure, higher temperature, and a denser medium pressing against every surface of the instrument. Communication would degrade in parallel with the descent. A probe sinking into Neptune's atmosphere would need to transmit its data upward to an orbiter or relay spacecraft above. As the probe descends, the atmosphere above it thickens. At some depth, the atmospheric column becomes opaque to radio frequencies, and the signal attenuates to the point of uselessness. The probe does not lose contact because of a malfunction. It loses contact because the planet itself closes around it, sealing off the transmission path the way water closes over a sinking stone. The last data received by the relay above would describe conditions the probe had already passed through by the time the signal climbed back out of the atmosphere. And then, nothing. The probe would continue descending, still measuring, still functioning, possibly for minutes or hours beyond its last transmitted signal, but the data would never leave the planet. It would be gathered and then buried, entombed inside Neptune by the same pressure that was destroying the instrument collecting it. The Galileo probe at Jupiter lasted 57 minutes and reached 23 bars. A probe at Neptune might last a comparable time or less, depending on its engineering, but the scientific return from those minutes would be extraordinary. Even a brief descent would provide the first direct measurements of an ice giant atmosphere, including composition data that could resolve decades-old questions about the ratio of heavy elements to hydrogen and helium, the depth and structure of the methane cloud layers, the temperature profile through the upper atmosphere, and the nature of the wind shear between the screaming upper layers and the slower rotating interior beneath. But every bite of that data would be a race against destruction. The probe descends, the pressure mounts, the temperature climbs, the signal weakens, and at some depth, which no model can predict with certainty because no probe has ever been there, the instrument fails. Not because of a design flaw, because the planet is stronger than anything we know how to build. The machine does its job for as long as the conditions permit, and then the conditions stop permitting. And the machine is folded into the interior of a world that has been crushing things for 4.5 billion years. That is what studying Neptune's interior would actually look like. Not a gentle survey, not a sustained orbital campaign with years of data return. A single, brief, one-way plunge into an atmosphere that has no flaw, conducted by a machine that knows from the moment of release that it will not survive the descent. Transmitting data upward through an atmospheric column that is actively working to absorb the signal, on a timeline measured in minutes, in total darkness, 4.5 billion kilometers from the nearest human ear. And even this, even a probe that is designed from the start to be destroyed, has never been attempted. No agency has built one. No mission has carried one. The technology exists in concept, but not in metal. That distance deserves its own reckoning, because the interior of Neptune is only half of the Unforgiving equation. The other half is the problem of getting there. And that problem is not merely difficult. For all practical purposes, with current and near-future technology, it may be effectively permanent. Consider what it took to reach Neptune once. Voyager 2 launched on August 20th, 1977. It arrived at Neptune on August 25th, 1989. 12 years. The journey was only possible because of a rare alignment of the 4 outer planets that occurs once every approximately 175 years. Voyager 2 used gravity assists at Jupiter and Saturn and Uranus to gain speed and redirect its trajectory toward Neptune. Without those assists, a direct flight to Neptune using the same propulsion technology would have taken decades longer. And Voyager 2 did not stop. It could not. The spacecraft carried no braking system capable of slowing it into orbit around Neptune. It flew past, collected data during a window of close approach, lasting less than a single day, and then continued outward, eventually crossing the boundary of the sun's influence and entering interstellar space. The flyby was a triumph. It was also a goodbye. No spacecraft has returned, and the reasons go beyond funding or political will, though those factors are real. The fundamental problem is physics. Neptune is far. Getting a spacecraft to Neptune requires either a very long travel time or a very large amount of energy, and inserting a spacecraft into orbit around Neptune, rather than simply flying past it, requires carrying enough fuel to decelerate from interplanetary cruise speed to orbital capture velocity. That fuel has mass. That mass requires more fuel to accelerate. The exponential nature of the rocket equation means that every kilogram of payload delivered into Neptune orbit costs many kilograms of fuel at launch. The Neptune Odyssey mission concept, studied and published by a team led by researchers at the Johns Hopkins Applied Physics Laboratory, proposed a flagship-class orbiter and atmospheric probe to the Neptune and Triton system. The architecture called for a launch in the early 2030s, using a Jupiter gravity assist to reduce travel time to approximately 12 to 16 years, with arrival at Neptune in the mid-2040s. The spacecraft would carry a suite of instruments to study Neptune's atmosphere, magnetosphere, ring system, and moons, with particular emphasis on Triton as a captured Kuiper belt object and potential ocean world. The concept was scientifically compelling. It addressed questions that have been open since 1989. It was reviewed as part of the Planetary Science Decadal Survey process, and it was not selected as the top priority. The Decadal Survey, published in 2022, ranked a Uranus orbiter and probe as the highest priority flagship mission. Citing the fact that Uranus is closer, the launch windows are more favorable, and the mission could be accomplished at a lower cost. Neptune was deferred. Again, the practical constraints are worth examining in detail because they reveal something fundamental about what Neptune's distance means for exploration. A mission to Neptune using a Jupiter gravity assist requires the two planets to be in a specific orbital relationship. These windows are not annual. They occur in cycles separated by more than a decade. The optimal window for a Neptune mission with a Jupiter gravity assist was projected for 2029 to 2030. That window is passing. A subsequent window would open later, but each missed opportunity pushes the arrival date further into the future. The spacecraft itself would need to be powered by radioisotope thermoelectric generators. Because solar panels cannot produce meaningful electricity at Neptune's distance from the Sun. At 30 astronomical units, sunlight is roughly 1/900th as intense as at Earth. Solar panels that could power a spacecraft at Mars are useless at Neptune. This means the mission requires plutonium-238, a radioactive isotope produced in specialized facilities that have been operating below capacity for years. The Decadal Survey acknowledged that a shortfall in plutonium production could delay the Uranus mission to the mid or late 2030s. A Neptune mission, competing for the same limited fuel supply, would face the same constraint or worse. And even if the mission launches on time, even if the gravity assist works perfectly, even if the spacecraft survives a cruise phase lasting more than a decade, the operational challenges at Neptune are formidable. Communication with a spacecraft at Neptune involves a round-trip signal delay of over 8 hours. A command sent from Earth takes more than 4 hours to arrive. The confirmation takes more than 4 hours to return. Real-time control is impossible. Every maneuver, every instrument adjustment, every response to an unexpected situation must be pre-programmed or handled autonomously by onboard systems. The Voyager team dealt with this problem in 1989 by planning the flyby sequence years in advance and uploading detailed command sequences to the spacecraft before the encounter began. An orbital mission would face this challenge continuously for years, around a planet with a chaotic magnetic environment, transient storm systems, and moons that require precision targeting for close flybys. The engineering is not impossible. The Cassini mission operated around Saturn with signal delays of over an hour each way, and performed brilliantly. But Neptune's delay is 4 times longer, and the margin for error narrows with every additional hour of communication lag. There is another factor that rarely enters public discussion: the thermal environment. Spacecraft operating in the outer solar system face extreme cold. At Neptune's distance, the ambient temperature in shadow approaches minus 230 degrees Celsius. Instruments, electronics, and mechanical systems must be kept warm enough to function, and the only heat source available in deep space is the spacecraft's own radioisotope generators and electrical heaters. Thermal management for a Neptune orbiter is a significant engineering challenge, one that drives mass, power, and design complexity in ways that compound every other constraint. The sum of these obstacles is not that a Neptune mission is impossible. It is that a Neptune mission is one of the most difficult things humanity could attempt in planetary exploration. Harder than Mars, harder than Jupiter, harder than Saturn, comparable in difficulty only to a mission to the interstellar medium itself. And the reward, in terms of close-range data from one of the least understood planets in the solar system, would be extraordinary. But the cost, the timeline, the technological demands, and the competition for resources from other scientifically compelling targets mean that Neptune will remain unvisited for the foreseeable future. China has proposed a Neptune orbiter concept as part of its deep space exploration roadmap. The concept remains in early planning stages, with no confirmed launch date or detailed mission architecture publicly available. If it proceeds, it would represent the first dedicated mission to Neptune in history. If it does not proceed, Neptune will continue to be studied exclusively from a distance of 4.5 billion kilometers, using telescopes that can resolve features no smaller than several thousand kilometers across, supplemented by data from a flyby that occurred before the fall of the Berlin Wall. This is the second layer of Neptune's hostility. The first was the atmosphere, the winds and storms and magnetic chaos that make the planet's exterior violent. The second is the interior, the crushing pressures that remake matter into substances that should not exist. The diamond rain that falls through darkness no light will ever reach. The superionic water that generates a magnetic field through mechanisms only confirmed in laboratories within the last few years. And the third, which binds the first two together, is the distance. The sheer, grinding, implacable distance that turns every attempt to study this planet into an exercise in patience, precision, and compromise. Neptune is not merely a hostile destination, it is an almost unreachable one. A world where the atmosphere would destroy any probe within hours, where the interior would crush any material within minutes, and where the journey to arrive takes longer than many human careers. The violence is real, the strangeness is confirmed, and the isolation The 4+ hours of light-speed silence between this planet and the nearest human ear is absolute. But even all of this, the winds, the pressure, the diamond rain, the superionic water, the tilted magnetic field, the decades of travel, does not fully capture what makes Neptune the most unforgiving planet in the solar system. Because the deepest form of hostility is not physical, it is emotional. It is the realization that this planet exists at a distance and a scale and a level of indifference that makes human presence not just dangerous, but meaningless. And that realization, the one that separates Neptune from every other world we have discussed, is where this story arrives next. There is a test you can run on yourself. Close your eyes and try to picture Jupiter. Most people can do it almost immediately. The bands, the swirling storms, the great red spot, that enormous eye staring out from the southern hemisphere like something alive. Jupiter dominates the imagination because it dominates the sky, the solar system, and every photograph ever taken of it. It is massive. It is dramatic. It looks like something that has opinions about your existence. Jupiter is the planet that feels like it could notice you. Now try Saturn. Easier still. The rings define it. Even a child who has never taken a science class can draw Saturn, a circle with a line through it. The universal shorthand for planet. Saturn is beautiful in a way that is almost unfair to the other worlds. The rings give it a visual identity so distinctive that no other object in the solar system can be confused with it. Saturn is the planet that looks like a piece of jewelry. Now try Mars. The red surface, the canyons, the volcanoes, the rovers crawling across the dust, sending photographs that look almost like Earth deserts if you squint. Mars is the planet that feels reachable. We have driven on it. We have scooped its soil. We have flown a helicopter in its atmosphere. Mars is the planet that invites human projection. People plan to live there. Companies sell tickets. Mars is the planet that says maybe. Now close your eyes and try to picture Neptune. What appears? For most people, the answer is a vague blue circle. Maybe a sense of cold. Maybe a feeling of distance, but no storms with names. No rings that define a silhouette. No surface features. No rovers. No human-scale stories. Neptune exists in the imagination as an abstraction, a color, and a position in a list, not as a place with texture, danger, or emotional weight. This is the final and most fundamental layer of what makes Neptune unforgiving. It is not just that the planet is physically severe. It is that the planet exists beyond the reach of human emotional engagement. It is too far to see without a telescope, too far to visit without decades of travel, too far to communicate with in anything resembling real time, too strange in its interior to model with everyday intuition, and too absent from the cultural record to have accumulated the kind of narrative familiarity that makes other planets feel like places rather than data points. Jupiter is frightening. Everyone knows that. Its radiation belts can kill an unshielded human in minutes. Its gravity well is a trap that has captured more than 90 moons. Its atmospheric pressure increases without limit as you descend, and as we saw earlier, the only probe ever sent into its clouds was crushed and silenced within an hour. Jupiter is deadly, and everyone understands this, because Jupiter has been studied, orbited, photographed, and written about for centuries. Saturn is dangerous in its own way. Its radiation environment is less extreme than Jupiter's, but its ring system and moon system present gravitational hazards that demand precision. The Cassini spacecraft spent 13 years navigating Saturn's system, threading between moons and ring gaps, and when its mission ended in 2017, it was deliberately plunged into Saturn's atmosphere to avoid contaminating the potentially habitable moon Enceladus. Saturn's dangers are known because Saturn has been studied long enough for its dangers to become part of the scientific narrative. Even Uranus, the other ice giant, has a strangeness that gives it emotional traction. It's tilted on its side, rolling around the sun like a ball rather than spinning like a top. That tilt gives it extreme seasons, with each pole spending decades in continuous sunlight, followed by decades in continuous darkness. Uranus is weird, and weirdness is a form of engagement. People remember the tilt, they remember the name, they remember something. Neptune has no comparable hook. Its storms come and go without the permanence of Jupiter's great red spot. Its rings are too faint to define its silhouette. Its tilt is moderate, nothing like the dramatic sideways roll of Uranus. Its moons are fascinating to planetary scientists, but unknown to the general public. Triton, the largest, is a captured Kuiper belt object with nitrogen geysers and a retrograde orbit, and it is one of the most scientifically interesting moons in the solar system. But Triton does not occupy the cultural space that Europa, Io, Titan, or Enceladus do, because no dedicated mission has ever studied it, and its parent planet does not generate enough public attention to carry its moons into broader awareness. The result is a planet that is simultaneously one of the most extreme worlds in the solar system, and one of the least emotionally present. And that combination is what makes Neptune uniquely unforgiving, in a sense that goes beyond physics. Consider what unforgiving actually means. The word implies not merely severity, but the absence of something. Forgiveness is the act of making room for error, for weakness, for the imperfect attempts of a being that is trying. An unforgiving environment is one that makes no such room. It does not accommodate. It does not bend. It does not notice the difference between a careful attempt and a reckless one. It responds to both with the same indifference. Jupiter is hostile, but Jupiter engages. Its great red spot has been watched for centuries. Its moons have been mapped and named and studied by missions that spent years in orbit. Jupiter's hostility is the hostility of something that is present, something that looms in the sky and demands attention, and responds to observation with detail and complexity that reward the effort. Jupiter is dangerous the way a bonfire is dangerous. You can see it. You can feel its heat. You can respect it and still approach it with caution and learn from it and even find it beautiful. Neptune is hostile the way deep ocean is hostile, not because it attacks, because it does not care, because it exists at a depth and a distance and a pressure that makes the question of human survival irrelevant. You do not negotiate with the deep ocean. You do not impress it with your preparation or your technology. You enter it understanding that it will not adjust itself by a single degree or a single atmosphere of pressure to accommodate your presence. You are either capable of surviving the conditions as they are, or you are destroyed. There is no middle ground. There is no mercy. There is no relationship. Neptune offers the same terms. The winds will not slow down because a probe has entered the atmosphere. The pressure will not ease because an instrument is approaching its crush depth. The temperature will not moderate because a spacecraft's heaters are running low. The distance will not shorten because mission controllers are anxious about a signal that has not arrived in 8 hours. Neptune does not interact with human effort. It simply persists in its own conditions, at its own distance, on its own timescale, and the question of whether anything human can survive there is not a question Neptune is interested in answering. This is the quality that separates Neptune from every other planet in the conversation about severity. Venus is hotter. The surface temperature on Venus exceeds 460 degrees Celsius, hot enough to melt lead. The atmospheric pressure at Venus's surface is roughly 90 times Earth's. The atmosphere is composed largely of carbon dioxide with clouds of sulfuric acid. Venus is, by many measures, the single most lethal surface environment of any rocky planet in the solar system. But Venus is close. It is roughly 40 million kilometers from Earth at its nearest approach. A spacecraft can reach Venus in a few months. Multiple missions have landed on its surface and survived long enough to return photographs. The Soviet Venera landers operated on the surface of Venus for up to 2 hours. Venus is deadly, but Venus is reachable. Venus allows the attempt. Venus permits the brief, doomed, heroic gesture of landing and transmitting, before being destroyed. Neptune does not even permit the gesture. No probe has ever entered its atmosphere. No lander has ever touched any surface within its system. The closest any human-made object has come to Neptune is 4,800 kilometers, the distance at which Voyager 2 passed the cloud tops during a flyby that lasted less than a day. And that closest approach happened more than 3.5 decades ago. Mars, for all its hostility, its thin atmosphere, its cold, its radiation, its distance from immediate rescue, has been reframed by human ambition into a destination. People talk about living on Mars. They talk about building shelters, growing food, establishing a second home for the species. Mars is cold and barren and would kill an unprotected human in minutes, but it has a surface you can stand on. It has a day that is roughly the same length as Earth's. It has ice you could melt and soil you could study, and a horizon you could photograph at sunset. Mars, despite everything, offers handholds. Small, tenuous, difficult handholds, but real ones. Things a human imagination can grip and use to pull itself forward. Neptune offers no handholds. There is no surface. There is no horizon. There is no sky in any direction that is not made of thickening gas that transitions seamlessly into crushing fluid. The light from the sun at Neptune's cloud tops is a dim glow that fades to blackness within a few hundred kilometers of descent. There is nothing to stand on, nothing to see, nothing to breathe, nothing to build on, and nothing to push off from. The planet is a sphere of increasingly hostile fluid, wrapped around a core that no instrument has ever detected directly, rotating at a speed that drives winds faster than sound, generating a magnetic field from materials that exist nowhere else in human experience, surrounded by a vacuum so vast that a cry for help would take 4 hours to reach the nearest ear, and the answer, if one came, would take 4 hours to return. There is a particular kind of loneliness embedded in the 8-hour round trip. When Voyager 2 flew past Neptune, the scientists and engineers at the Jet Propulsion Laboratory experienced it firsthand. Every image, every data packet, every confirmation that the spacecraft was still functioning arrived more than 4 hours after the event it described. The team was watching a planet in the past tense. By the time they saw a photograph of Neptune's cloud tops, Voyager 2 had already moved thousands of kilometers beyond the point where the photograph was taken. The experience of observing Neptune through Voyager 2 was not real-time science. It was archaeology performed on events that were still warm. An orbiter at Neptune would face this delay continuously, For years, every command sequence would be uploaded and then waited on. Every unexpected event would be discovered hours after it occurred. Every correction would arrive hours after it was needed. Mission controllers would not be flying a spacecraft. They would be writing letters to one and waiting for replies. The emotional texture of such a mission, the daily experience of working with a machine that exists in a 4-hour past, would be unlike anything in the history of planetary exploration. Even the Cassini mission at Saturn, with its roughly 1-hour signal delay, maintained something that felt like a conversation. At Neptune, the conversation becomes a correspondence, and the correspondent is a machine circling a world that has no interest in being understood. This is where the idea of the unforgiving becomes complete. Neptune is not just a planet with extreme weather, extreme pressure, extreme cold, extreme distance, and extreme magnetic strangeness. It is a planet that resists comprehension in a way that the other giants do not. Jupiter is extreme, but Jupiter has been stared at long enough that its extremes feel familiar. Saturn is extreme, but Saturn's beauty creates an emotional bridge that makes its dangers feel approachable. Uranus is strange, but its strangeness has a single defining feature: the tilt that gives the mind a place to start. Neptune has none of these concessions. Its storms vanish before they can be named. Its interior is made of substances that exist for nanoseconds in laboratories. Its magnetic field follows rules that are still being written. Its distance defeats every attempt to build the kind of sustained, detailed relationship that makes a planet feel known. And its visual identity, a pale blue sphere with faint rings and no distinctive markings visible from Earth, gives the imagination nothing to hold on to. The result is a world that occupies a unique position in the solar system. Not the largest, not the hottest, not the most radioactive, not the most famous, but possibly the most completely and comprehensively inhuman. Every other planet offers some feature, some detail, some characteristic that allows a human mind to establish a point of contact, a surface to imagine standing on, a storm to imagine watching, a moon to imagine exploring, a ring to imagine orbiting through. Neptune offers a blue blur, a set of numbers that describe conditions no human body or machine has ever directly experienced, and a silence that lasts 4 hours in each direction. The 2022 Decadal Survey's decision to prioritize Uranus over Neptune was scientifically and logistically reasonable, but it also extended, by decades, the period during which Neptune remains the least visited planet in the solar system. Every year that passes without a dedicated mission is another year in which Neptune's secrets age in the dark. The storms cycle, the diamond rain falls, the superionic water hums with ionic currents, the magnetic field tumbles and reforms with every 16-hour rotation, and none of it is observed, none of it is measured, none of it is archived in any database more recent than 1989. There is a sentence that planetary scientists sometimes use when discussing Neptune. They say that Neptune is the planet we know the least about. That sentence is accurate, and it is also incomplete. Because the reason we know the least about Neptune is not that the planet is uninteresting. It is that the planet has made knowing it as difficult as anything in planetary science can be. The distance is the maximum among the major planets. The communication delay is the longest. The launch windows are the narrowest. The energy requirements are the highest. The travel time is the longest. And the data we have from close range is the oldest. Neptune has not hidden from us. It has simply existed on terms so extreme that our best efforts to reach it have produced exactly one flyby and 35 years of telescopic guesswork. The planet is not withholding information. It is surrounded by the kind of distance, the kind of pressure, the kind of magnetic chaos, and the kind of atmospheric violence that makes gathering information an act of extraordinary ambition. And when the ambition succeeds, as it did in 1989, the reward is a glimpse so brief that it raises more questions than it answers, and then it is over. This is what Unforgiving looks like when you strip away the drama. It is not a monster planet that roars and threatens. It is a world that exists in its own severity, at its own distance, in its own darkness, and does not modulate any of those qualities by a single degree in response to human curiosity, human technology, or human need. Jupiter at least gives you a show. Saturn at least gives you beauty. Mars at least gives you hope. Neptune gives you conditions, measured once, 35 years ago, by a spacecraft that was never coming back. The conclusion of this story is not that Neptune is the scariest planet. Fear requires proximity. You cannot be afraid of something you cannot see, cannot reach, and cannot meaningfully imagine. The conclusion is that Neptune is the most thoroughly indifferent planet in the solar system. It combines every form of physical hostility, wind, cold, pressure, distance, magnetic chaos, exotic chemistry, into a single world that sits at the very edge of the sun's influence and offers nothing back. No surface to land on, no atmosphere a probe could survive for long, no communication window shorter than 8 hours round trip, no easy orbit, no return ticket, no beauty visible to the naked eye, no cultural presence, no emotional resonance, no handholds of any kind, and perhaps the most disquieting realization of all is this: Neptune is not unusual in the universe. It is unusual in our solar system, where ice giants are outnumbered by rocky planets and gas giants. But in the broader galaxy, planets the size and type of Neptune appear to be among the most common. Surveys of exoplanets have revealed that sub-Neptune and Neptune-sized worlds are extraordinarily prevalent around other stars. The galaxy may be filled with planets like this one: cold, distant, wind-scoured ice giants with crushing interiors and bizarre magnetic fields, orbiting their stars at distances that make observation difficult and arrival nearly impossible. If that is the case, then Neptune is not an anomaly. It is a template. The most common kind of large planet in the galaxy may also be the kind that is most resistant to human understanding, most hostile to human technology, and most indifferent to human ambition. The universe may be filled with worlds that look from a distance like faint blue dots, and that contain beneath their calm exteriors the same merciless combination of wind and pressure and darkness and distance that makes Neptune what it is. We began this story with the observation that Neptune is the planet most people forget. That forgetting is not a failure of education or attention. It is a natural response to a world that gives the human mind nothing to work with. No drama, no beauty, no accessibility, no story, until you look closely enough to see what the silence actually contains. What it contains is a world of supersonic wind moving through a twilight that fades to permanent darkness within a few hundred kilometers. A world where methane is ripped apart and its carbon is forged into diamonds that rain through hot, pressurized fluid for thousands of kilometers, before settling onto a core that may be wrapped in a shell of crystallized carbon. A world where water is crushed into a form of matter that is simultaneously solid and liquid, conducting electricity through a lattice of frozen oxygen, while hydrogen ions stream freely through the gaps. A world whose magnetic field is tilted nearly halfway to sideways and offset from its own center, producing a magnetosphere that tumbles through space with every rotation. A world so far from the sun that light takes over 4 hours to arrive, and a spacecraft takes over a decade. A world visited once, briefly, by a machine that was never designed for it and never returned. Neptune is the most unforgiving planet in the solar system, not because it is the largest or the most dramatic or the most lethal in any single category. It is the most unforgiving because it combines every form of hostility into a single world, and then places that world so far from human reach that even observing the hostility requires the full extent of our technological capability. Other planets are dangerous. Neptune is dangerous and indifferent and unreachable and unknown, all at once, all the time, in every direction. The most unsettling truth about Neptune is not any single measurement. It is not the wind speed or the pressure or the temperature or the distance. It is the realization that one of the least central planets in human imagination may also be one of the clearest examples of a world that gives nothing back to the idea of human presence. Not because it is malicious, not because it is hiding something, but because it exists on terms so far removed from anything human that the concept of presence, of survival, of mattering simply does not apply. Neptune does not reject us. It does not even notice us. It turns in the dark, 4.5 billion kilometers away, wrapped in winds we measured once, powered by heat we do not fully understand, filled with materials we can only create for nanoseconds, orbited by a captured moon we have never studied up close, and surrounded by a silence so vast that even our fastest signals take hours to cross it. The planet is there. It has always been there, and it will still be there, long after the last telescope is pointed somewhere else, long after the last mission proposal is filed and forgotten, long after the last human being who remembers Voyager 2's 12-year journey has stopped looking up at the night sky. Neptune does not need to be remembered. It does not need to be understood. It does not need anything from us at all. And that, more than the wind, more than the cold, more than the crushing dark, is what makes it the most unforgiving planet we know.